So good evening, everyone. Hope I'm audible to every participant and guests over here. Uh, Wonderful to see you once again. Before we start off with this workshop, I would request Dr. Kaushik Mitra, who is our revered Secretary General of IPHA, to say a few words.
Thank you, Dr. Shivaji Gupta, and good evening, everyone. It's very nice to see all of you today here, gathered here for IPHA Master Class once again, and this is in online mode. I can see many of my friends who are here. Thank you all for joining this much awaited workshop. To accommodate all of you, we have shifted from offline to online mode. And I would like to thank our coordinators for this workshop. Along with me, I had Dr. Ribhu Basu with me, who is the Joint Secretary of Indian Public Health Association and working in All India Institute of Hygiene and Public Health. To accompany, we have Dr. Shivaji Gupta, who has already introduced to you. He is coordinating the workshop and he is working as assistant professor in Minnapur Medical College. We have Dr. Arnav Sarkar, who is working in the Directorate of Health Services in West Bengal, and Dr. Devdatta Haldar, working as assistant professor in Diamond Harbour Government Medical College. So they are our coordinators for the workshop. And we have Dr. Shumon Guho as our facilitator for this workshop. He will be there all through the workshop in the next 6 sessions. We have placed sessions not every day, but to give you some few days of gap to grasp the subject. So we have Dr. Shumon Guho, who is working with the Presidency University, and he will be with us all throughout the workshop. Thank you, sir, for being the facilitator of our workshop. And thank you, all of you. I will be also there with you in some of the sessions to learn something. Thank you all. Over to Dr. Shivaji.
Thank you, sir, for the kind and encouraging words. Before we start off, I would like to introduce Dr. Guho, Dr. Shumon Guho, who is currently working as assistant professor at Presidency University. He holds a PhD in statistics from Indian Statistical Institute and has more than 10-20 publications in high impact journals and a very experienced teacher in his domain. So without any further ado, I will ask sir to start the session. But just a note that this recording will not be shared with anyone. So all who are interested to study this topic are requested to attend the sessions live. Please don't request us for the recording as it won't be available. Thank you very much. Over to you, sir.
Thank you, Dr. Gupta. I hope I'm audible to all of you.
Yes, sir.
Okay. So firstly, I thank Dr. Ribhu Basu and other esteemed member of IPHA for inviting me to take these classes. But before starting the class, I just want to make sure one thing, that the sole objective of these 6 classes would be to make sure that after attending these classes, you should be able to do your own statistical analysis using the statistical computing software, and you don't need to go to a statistician for doing that. Of course, that would be kind of a bad situation for we statisticians, but still, I want that after attending these 6 classes, you should be able to do the time series analysis, at least the time series analysis of time series data using computational statistical computing softwares. Okay, and also before starting the class, I just want to say something that please feel free to stop me because there will be 6 sessions, so we are not in a hurry to complete everything in a single day. Okay, I think Dr. Shukona she's saying that she cannot hear any sound. So am I audible to others?
Yes, sir.
Yes,
sir.
Dr.
Okay.
Sugarna, will you please log
Yes,
out and
sir.
log in again?
Okay, so maybe it's a problem from her network or from her side. So I'd request her to log out and then rejoin once again. Okay, so maybe we can start today's class. So before starting the class, I have already shared the schedule for the 6-day workshop, but still I just want to reiterate everything once again that in today's class, I just plan to introduce a statistical computing software, which is called the Jamovi. In the next class, we'll be introducing another statistical computing software, which is R and RStudio. Those are, in a sense, a combined package. And then the third class, I'll teach basic time series models. In the fourth class, I'll be using mostly Jamovi and a little bit of R and RStudio to demonstrate basic time series analysis. Then in the fifth class, I'll be discussing aspects of more advanced kind of time series modeling, the regression time series model and the multivariate time series model. And then in the last and the sixth class, we'll be doing hands-on practical for the multivariate and more advanced kind of time series model using RStudio. Okay. So I'll be happy that I'll be very happy if you are interactive in this classes. I know that in online sessions generally people don't respond much, and but still I'd be very happy that if you say something, say some feedback from your side, or if you have any difficulty in understanding any step, please. I'm just requesting all of you, please feel free to stop me. Okay, we have a lot of time. Okay, so let us start today's class. So I have already told you to install the Jamovi software. So have all of you been able to install the Jamovi software?
Yes, sir.
If not, those who haven't yet been able to install the Jamovi software in your system, so I'll request all of you to just open your browser, type Jamovi. That will guide you to the corresponding website. From there, you can install the Jamovi software. Now, there in the website, you will see two versions of Jamovi. One is the solid version, and another one which is like a working version, which is more improved. But of course, that is like the beta version of the Jamovi software. In generally, if you are using Jamovi to carry out your research uh, and then if you want to communicate that research for some publication, then you should always be using the stable version or the solid version, because the solid version is foolproof version of Jamovi. On the other hand, for this particular course, I'll be using the other version, the more updated, the beta version of Jamovi software. That is because the solid version of Jamovi or the stable version of Jamovi doesn't contain packages for time series data analysis. But since it is a workshop on time series data analysis, so I have to work with the beta version of Jamovi. However, for doing usual kind of statistical analysis like t-test or univariate data analysis, regression, or other kind of statistical analysis, one doesn't need the beta version of Jamovi. And actually, it is recommended uh, if you are going to use the software to for your research, and then if you are going to communicate it, it is always better to avoid beta version softwares because they contain some bugs, and so uh, mm, those findings may be questionable. Okay, okay. So let me share the Jamovi screen with all of you. So can you see the Jamovi screen?
Yes, sir.
Okay.
Yes, sir.
Okay. So all of you, please click and open the Jamovi. Okay. All of you, please click in your desktop and open the Jamovi software. Actually, I have shared one data set in the common WhatsApp group. So have you been able to download that dataset in your system? So are you ready with that dataset? Or if not, please download it now. So we may wait for 1 or 2 minutes so that others who haven't downloaded it yet, they can download it and make completely prepared for the hands-on. It will be kind of an hands-on learning, because there is no way one can learn a software in a theoretical sense, but it should be an hands-on approach. So I'll ask all of you to carry out the same operation in your system using the Jamovi installed in your system, and have a fast and flavor of how to work with the software. Okay.
Sir, can you share the dataset again? Because I joined the group later and it's not visible.
Okay. Yeah, sure. I'm sharing it once again.
Thank you, sir.
Okay, so I have shared the dataset once again. Yeah, maybe somebody else has already shared it once again. Okay, so you please download it, store the dataset somewhere in your system. So we'll have to use that dataset for the demonstration class. Okay, so we start, and maybe the others will catch up with us. So there in the left side in Jamovi, there are actually two panels. In left side, there is one panel, and right side, there is a blank screen. So both are actually the two panels. The left panel is actually needed for the input side. Okay. On the other hand, the right hand panel, this side, that is where you are going to get the output. So it's very simple. In the left hand side, you will give the input. In the right hand side, you will get the output of your statistical analysis. Okay, so then you go to the top corner, you search for, sorry. Okay. So you select the open, and there you'll see two options. The first option is data library. So by data library, actually we mean the Jamovi software itself contains some data sets. So these are like well-known data sets that comes as a part of this software installation. So those sort of data sets are available in this data library. So you can see this, right? So these are like the very popular kind of statistical data sets which comes with the Jamovi software itself. So later on, I'll choose maybe one of this data set to show some demo statistical analysis. But for the time being, I'll be choosing the data set that I have shared with you in the common WhatsApp group. So that means I'll be sharing, or I'll be going to open the shared data set. So you can see that when I press this PC button, so that there I can browse and I can navigate to that particular data set, which I have shared with all of you. I think there are some issues with the sharing part. Okay. So can you see the shared data set? So can you see the data set in the shared screen? Okay,
Yes,
so all of you must now be able to open this data set in your Jamovi software, right? Okay. Now you see, there are certain options at the top left hand corner. So there is a variable option. So this variable option will actually show you what are the variables related to this data set. Actually, there are 17 variables in this data set. You can see there are 17 variables, and these symbols, besides the name of the variable, they actually tell you what type of variable it is. For example, this symbol is actually meant for a continuous variable. On the other hand, this symbol, the gender, this is used when someone is working with a nominal variable. So gender is a nominal variable, so the symbol is like this. On the other hand, age, height, weight, these are all continuous variable, so they have a different symbols than the nominal variables. Okay. Now, what are the basic analysis that we can do? But even before doing any basic analysis, we just want to do some kind of coding. Okay. For example, suppose I want to code a new variable. Suppose this is a data set that is already available to me. Suppose I want to create a new variable. Okay. So for that, what I can do,
Sir, there is a question as to, would you please repeat how to import the data set?
okay, sure. Yeah, I'll just show you it once again. So you go to the top left corner. There you will see two options, new or open. So click the open button. Now under the open button, there are two options, this PC and then data library option. Now, if you click the data library, there will be some data sets that are displayed here. These are the data set that comes as a part of the Jamovi software itself. So these are other statistical data sets. However, we are not interested in inputting these data sets. Okay. But we are interested in that particular data set that I have shared with you in the common WhatsApp group. So I must have downloaded that dataset in my laptop and I have stored it some location. So I'll be choosing a dataset from my own PC. So that's why this comes under the heading this PC. Now under this PC option, you'll see there is an option called browse. So there is an option called browse, and under that option, so this is my data set, and I open the data file. So is it now okay to everybody that how to import the data set?
Yes, sir.
Okay. Now suppose I want to create a new variable. Okay. So there is an option of new data variable. So can you see in this column, there is a name that R. So that would be the name of the new variable. So I suppose I want to create a new variable, which is R. Now suppose I just want to change the name of the variable maybe. Then you can put the description of the variable here. Suppose
Sir, the
maybe
screen is
the
fixed
screen
at
not
variables only.
Hello?
Screen is not moving, sir.
We are seeing the variable list only, that's all.
Okay, okay. Yeah, maybe I can stop share and I can share it once again.
So kindly share the entire screen. Okay, so whenever you jump windows, it will
Okay,
reflect. Okay.
can you see the screen now?
Yes, sir.
Yes.
So can you see that the name of the variable is written data variable? Then I can put the description in this way.
So we could not see what you did to include a new variable.
Right, right. Okay, okay. I'll just go back to. So suppose I click on the top of the column. Okay, then there some questions are asked like, would you want to create a new data variable or you want to create a computed variable? For the time being, I'm just only interested in creating a new data variable. So I click here. So that means it automatically create a variable with a default name. So the default name will be using the English alphabet, but I just want to give some different name for that maybe. So I give a name demo variable. And then just so I just want to give some don't know what is happening here. Okay, yeah. So maybe I give a label as 1 and then I give a label as 2. So I enter the value 1 and 2. Okay. Then I'll quote the data in this way: 1, then 1, then 2, then 2, 1, 2, in this way. After coding it using this numerical values, I'll change that to some appropriate nominal level. For that, what I can do, so suppose 1 stand for male. So I'll change it to male. And then 2 stand for female. Then I change and press enter button. And that way I created a new demo variable. So is it now clear how to create a new variable which you can append with the dataset,
Sir,
the
I think
existing dataset?
there are some confusions.
Can you just show us once more, sir?
Yeah.
Just
So suppose I click the next column and I want to create another new variable. So I go to the new data variable and I click there. So now a new data variable is created named S. So the previous one was R. The next column is S, of course. Now you want your variable to have a legitimate name. So suppose you give it the name demo variable 2. Okay, so that would be the name. And then you want to change the labels. Okay, so you press the plus sign here and there a window will open prompting you to give the label value. Okay, now you can directly give level values like high, low, but then the problem is that then if you try to code the data here, you have to enter high every time, low every time, which is problematic. So that is why it is always a better practice to code the variable using some numerical value, enter those numerical value here, and then rename your levels to the appropriate categories. For example, suppose I give the level name 0, okay, and then I give another level name, say 4. So I'm just doing it randomly, 4, and then I give another level, maybe 7. So that means in this column, I have a nominal variable with 3 categories, and the first category is 0, the second category is 4, and the third category is 7. Now suppose I code the variable in this way: 0, next 0, then 7, then 7, then 0, then 4, then 7, like that. Now what I'll do, I'll change this 0, 4, 7, all these values to appropriate level. See, these are the dummy levels. These are not the actual levels of the variable we are interested in, but we have given this numerical value so that we can easily enter the data. So that is only for the sake of entering the data very easily. Now suppose 0 stand for low, 4 stand for mid, and 7 stand for high. So now it is coded in the appropriate manner that the first 2 data points are low, the next 2 data points are coded as high, then low, then mid, then high, in this way. So is it now clear that how to incorporate a new variable or code a new variable in your data set, the existing data set, because we often have to code a new variable in our existing data set. Is it now clear, or can I proceed with the next?
So next
part?
time to continue this data variables list, we have to put the numerical value only.
Right. So we have to
Sir,
put the numerical value first and then change them to appropriate nominal levels. On the other hand, if you are working with nominal data, suppose here the data set is nominal, but on the other hand, if you are working with the usual numerical data, then of course there is no data level. Then you can directly enter numbers like 1, 1, 2.5, 4.6, like that, likewise. So you can code both the new nominal variables as well as the numerical variable in this way.
Sir, I
Yeah.
have one question, sir.
Sure.
Sir,
Yeah.
in this way, what we are doing is basically we are entering new data. Like we
Right.
are creating new variable and we are entering that data.
Right.
Now, if we already have a variable, like in this case, we already have a variable like gender.
Right.
So if now we want to code gender from male and female to 1 and 2, so how would we do that?
Okay. Okay. Yeah. Right. So suppose I go to the first column, right? I click there and it is showing you every details about the variable. Okay. So see the so you can click there. Just yeah. So you can go to the first column, which is actually giving us the gender information, and it is coded in female, male in that way. So everything is written in detail here, that your variable is the name of the variable is gender, the data is a nominal variable, and what are the levels? There are 2 levels in this nominal variable. The one level is the female and the other level is male. Now suppose I want to code female as 1, then what I'll do, I'll just simply click there and put an 1 and put enter. And then suppose I want to code male as 7. So can you see that it is coded in this way, 11777. So is it answering your question?
Yes, sir, definitely. Thank you, sir.
Okay. Yeah, sure.
Sir,
Yeah,
Now I have a question that now it is the case of a nominal.
right,
Now, if it is a continuous
right.
variable, now how will we categorize that? Like say age.
Right. In that case, you have to work with the formula, the computed variable. So that means you already have data and you just want to turn them into categories, right?
Yes, sir.
Yeah. I think that is doable under the not the computed variable part, but I think this is under the transform part. The source variable is
It is not audible, sir.
yeah. No, I'm not saying anything, but actually I'm trying to give something there. Okay. Is greater than 40. Less than 40. Yeah, actually, yeah, right now I'm unable to do the coding, but I think it should be doable under this transform option. Okay.
Sir, we can do it later also. So we can keep this in mind. Okay.
Right, right,
So
right.
yes,
So,
yes,
yeah,
fine.
sure, sure.
So
So,
it can be done. I just tried. So
yeah,
if you want to um if you want to classify it, it should be that the things are not overlapping.
right,
And also, for example, if you want to classify age, so your first condition, if it is less than equals to 30, use 1. If it is
right,
less than equals to 40, use 2. So it does take 31 to 40 as 2, not 0 to 40. Like in SPSS, we find that if
right,
we take less than 40, it calculates 0 to 40. So it's not like that. and else use 3. So it can be classified as 1, 2, 3.
Okay, yeah, thank you.
Welcome, sir.
Okay, so so that means we can transform or categorize continuous variable using this transform option. For the time being, let undo all the previous steps and let go back to the original data set. Okay, yeah. Another thing that I just want to mention that suppose you are suspicious about certain values of your data set. For example, I'm just hypothetically saying that the value 1.5 that may not be a correctly measured value. So you want to treat the value 1.5 under the height variable as a missing data. So what you can do, so in that case, you can add the missing value and then press. So that means whenever under this height column, the value 1.5 appears, the Jamovi software will treat that as a missing value. So it will fade that particular value. So you can see that, right? So in that way, you can quote some values in your data set as the missing values. Okay. Okay, so now suppose I just want to do some basic computation based on the given data set. Suppose I want to calculate the mean of the 3 variable age, height, and weight. So what I can do that? How can I do that? So let's press this compute button. So a new column would be created just beside this, and there you can calculate the mean of the 3 columns. Okay, so let us see how we can do it. So suppose give a name. So this is the name of the new variable, and I want to calculate the mean. Okay, so certain options of functions are available, and since mean is a statistical function, I have to search it under the heading statistical function. So there I will get the mean. I'll press it 2 times, and then under mean, I just want to mention what are the variables which you should consider for calculating the mean. So I want to consider the variable age, and then put a comma, which will work as a separator, and then press height, and then put another comma, and then weight. So with that, now we press the enter button, and that should give me the mean value of these 3 columns. Okay, is it okay?
Yes, sir.
Okay.
Yes, sir. Yes.
Now you can notice one thing, that the new variable that we have created, there are certain empty cells. And what is the reason? The reason is that while calculating the mean of age, height, and weight in the second row, there is a missing value for the variable height. So it was not able to calculate the mean of the 3 values. In this situation, what we can do, we can ignore the missing value and calculate the mean based on only the age and weight. For that, I have to modify the formula a little bit. So I have to give an instruction to the Jamovi software that you should ignore the missing value. Now, if you put ignore underscore missing equal to 0, so that means it won't ignore the missing value and it will consider the missing value, and no value will be returned at this empty cell. So you can see that if I put 0 here, you'll get that. Okay, so the same value, the value is not changing. On the other hand, if you give any non-zero number, say 1, you'll see that it will actually ignore the missing value and calculate the mean only based on age and weight for this particular row. Then again, in the third row, since all the 3 values are available, it will calculate the usual mean. Okay, only for the second row or the other subsequent rows where certain missing value, the missing values are ignored and the mean is calculated based on the rest of the data. So this is an instruction for ignoring the missing value present in the data. Okay, so is it okay?
Sorry, sir, just 1 minute. Actually, for ignore missing is equal to 0 will not give you the mean value.
Right, because
And
anything, if you put anything non-zero, it will ignore the missing value and give you value in those cells. You can put also 3, 2, whatever. Okay, it doesn't matter. It won't change. But if you give 0 value, then it will be ignored.
thank you, sir.
Okay. Okay, so let us again undo all the previous operations and go back to the original data set. So these are the some basic operations or basic data coding that can be done using the Jamovi software. In the next step, what we will be doing after this coding is done, after this cleaning is done, the next step that we are interested in carrying out statistical analysis. Okay, so for that we have to go to this analysis tab. Okay, and there you will see many options are there. But before moving into the statistical analysis part, let me tell you that although there are some of the statistical analysis are available directly with the Jamovi software, some more advanced statistical analysis they are not directly available under Jamovi software. To carry out those more advanced kind of statistical analysis, you have to download and install appropriate packages. So you can do that under the option modules. Can you see the plus sign in the right hand side? So in the right hand side on the right panel, so there you click there. So it will show you what are the installed modules. Okay. So you click the Jamovi library option. Okay. Have you been able to go to this screen?
Yes, sir.
Okay. So there, under the available option, all the packages are the description of the packages are given there. So you may see some of the packages which may not be available for this particular version of Jamovi. However, for the rest of the or the most of the packages, you'll see there is an option for install button. So what you can do, you can click on this install button and then that will be installed with the current version of Jamovi. For example, suppose I just want to install this one. Yeah, okay. So can you see that one extra menu icon is there now in the top panel? So as you keep on installing new packages which are appropriate for the kind of statistical analysis you want to carry out, the more the new icons will be keep on adding in the top part of the panel. Okay. So Also, these are the installed, suppose after doing some statistical analysis, some particular package or some particular module is not needed anymore. So what you can do, you can remove it. So really uninstall this particular module that I have just installed. I press OK, and that would be uninstalled from the Jamovi system. So you can install these packages. I have installed a few packages in my machine. So you can also install similar packages depending upon what is your requirement. Okay. Now let us do some basic statistical analysis with the Jamovi software. The first thing that I want to do is some basic descriptive statistics or exploratory analysis from the data. Okay. So let us go to that. So go to the exploration part and then descriptives. Under the exploration button, you have option of descriptive. Now all the variables are available here. Suppose I choose this height variable. By the way, my screen is visible to everyone, right? I hope.
Yes, sir.
Okay. So suppose I choose this height variable, and then I want to carry out basic statistical analysis, or I want to calculate basic summary statistics of this height variable. So you just click on this height variable and press the arrow. So that will include your variable in the data set. And immediately you'll see that the basic summary statistics is presented in the right hand panel. So can you see that this is the number of data set, number of data points in the under this particular variable, the height variable. Then there are missing data. 3 missing data are there. A mean is calculated, median is calculated, the standard deviation, which is a measure of dispersion, that is also calculated, the minimum and the maximum value is calculated. Okay. However, these are some of the very basic summary statistics, but there are options for calculating even more sophisticated summary statistics related to this particular variable. So you will see under the option statistics, you'll see they will give you a whole set of option for calculating the summary statistics for this particular variable. And as you can see that for the time being, the mean and median is included. So that's why they're showing you the value of the mean and median. You can also include the mode. And if you click on the mode, the modal value will also be present in the table. And if you are interested, you can also calculate the quartile values. So quartile values actually represent those points which divide the data set into 4 quarters. So these are the basically the 25th percentile or the first quarter. This is also called the first quartile, the 50th percentile or the second quartile, and the third quartile or the 75th percentile. You can also calculate certain summary measures of skewness to see whether the data is symmetrically distributed. So the skewness value, so that means the data is negatively skewed. And you can also calculate some measure of kurtosis. So it is giving you the value of the kurtosis. Sometimes we are interested in checking whether our data set is there are other options of other measures of dispersion like variance, range, interquartile range. So all of them can be calculated. All of them can be calculated. Okay. Now, sometimes it is of interest to us to check whether the data is actually coming from a bell-shaped curve or a normal distribution, because the statistical theory that we apply, the significance level that we calculate, all are based on the assumption that the data is coming from a bell-shaped curve or a normal distribution. However, under certain in some kind of or some circumstances, it happens that the data is actually not following the normal distribution. So it is important to check whether the variable that you are considering that is normally distributed or not. If it is not normally distributed, then while reporting the statistical findings or while reporting the significance level, you have to be extra careful, because the usual kind of statistical techniques like the z-test or the t-test, they may not be appropriate, or the usual kind of ANOVA model, they may not be appropriate. The usual linear regression, they may not be appropriate. So that's why it is very important to check whether the data is coming from a bell-shaped curve, or it is coming from a normal distribution, or at least coming from an approximately normal distribution. Then whatever the statistical finding, that would be appropriate. On the other hand, if the data is not coming from a normal distribution, then even if you report significance level, even if you report some p-value, they may not be giving you the right idea about the underlying population. So your statistically significant finding may actually be insignificant. Okay. So that's why it is important to check normality. So there is an option for that also. So you can check the Shapiro-Wilks test for normality, and it is showing that it is not normal. Okay, so the hypothesis of normality is rejected. Okay, you can see from there. Okay, you can also calculate the outlier observation, the outliers. So suppose I take the most extreme 5 values as the outliers. Okay, so that means these are the most extreme highest values, and these are the most extreme lowest values. So altogether 5 highest values and 5 lowest values are identified as an outlier in the dataset, and the corresponding value is reported. Also the row where that particular value occurs, that is also reported here. Now suppose you just don't want to report the 5 extreme values, but rather 10 extreme values. So then you can change that value 5 to 10. Sorry. Any? Is an option, but somehow it is not working here. Yeah. Okay, so this will give you the basic summary measures for the height variable. Now suppose I just want to see some graphs, like the usual plots related to a single variable. So those options comes under the plot button. So under the plot button, what you can see the histogram of the data. The histogram of the height variable. So can you see the histogram of the height variable?
Yes.
Okay. So sometimes we are not interested in only in the histogram, but rather a smooth version of the histogram. The problem is that although this particular histogram is of quite good shape, but it happens that sometimes the histogram is too much contains too much zigzag pattern, and from there getting any idea about the underlying data may be quite difficult. So that's why under that situation, instead of working directly with an histogram, we want to work with a smooth version of the histogram, which is called the density, or the density estimate. Okay.
So there
you
is
can
a question about interpreting Shapiro-Wilk test.
Okay, okay. Yeah. So the meaning of the Shapiro-Wilks test is that you want to check whether your data is normally distributed or not. Okay. Now, if the p-value is very small, then the null hypothesis, which is the data is normally distributed, that is rejected. As in our case, we can see that the Shapiro-Wilks p-value. So there are two options like Shapiro-Wilks W, which is the Shapiro-Wilks test statistic, but we generally don't use the test statistic and take a statistical table to calculate the cutoff value and perform the test in this manner, but rather we prefer to work with p-value. So that's why for us, this Shapiro-Wilks W value doesn't matter anything, or it won't be of much importance. Okay, rather we are interested in checking only in this Shapiro-Wilks p-value, and you can see that the p-value is very small. So that means your H0 is rejected. P-value very small is your H0 is rejected. That means your data is coming from normal distribution. That hypothesis or that belief is rejected. So that means your data is really not normally distributed. So that is the interpretation of the Shapiro-Wilks test and the corresponding p-value. So it is basically a test of normality. So you check whether your data is really coming from a normal distribution. Now, if your data is not coming from a normal distribution, that means while reporting the statistical findings, you have to be extra careful. Does that answer the question?
Madam, will you please say if you have any doubts?
Yeah,
Shubham,
please,
yeah.
please, please tell me whether. Okay, okay. So if you have any doubt, please, let me know. Okay. Now,
Sir,
yes.
one thing I just want to know that the histogram, actually, it will show the AP curve also.
What?
The AP curve. I mean, if any data related to.
Okay. So, as Sir is from a statistical background, basically epidemiological curve is like we are plotting the number of cases per day. Okay. Okay. So, like we can plot it by time trends also, which you will know, because whenever you are plotting number with time, like line diagram suits best, but you can do it by histogram also if you want.
Okay.
That's, I think that answers your question, sir.
Sir. Okay.
Okay, thank you.
PNC card.
Okay. So we can also plot some other kind of univariate summaries, like we can see the box plot. It is actually very popular, the box plot. Okay. So you can also plot the data points itself together with the box plot. That option is also there. So I think all of you know about, have some idea about the box plot. So these are basically the quartiles of the data set. So this middle line is the second quartile, which splits the whole data set into two half, or in other words, it is basically the median. Then this is the third quartile, which above the third quartile, 75% of the 25% of the data will lie, and below the third quartile, 75% of the data will lie, and this is the first quartile. So basically, when we look into the box plot, it gives us the idea about the three quartiles, which divides the data into 4 equal quarters. Now, there is an option to show the data sets also, but this data are in a jittered form. So getting an impression about how the data is distributed may be difficult. So there is also an option to show the data points in a stacked form. Okay. And as you can see that in the near the median or the second quartile, the data are very much concentrated. Okay. Another thing that we want to plot while dealing with univariate data set or univariate data set is that QQ plot. So it is something like a Shapiro-Wilk test. Okay. So let me show you the QQ plot. So basically, QQ plot is the graphical version of Shapiro-Wilk test. So Shapiro-Wilk test is actually a formal statistical testing procedure that tells you whether your data is coming from normal distribution or not. On the other hand, QQ plot tells you whether your data is coming from a normal distribution or not just by showing you a graph. So if your data is really coming from a normal distribution, what would happen that all these data points should lie on a straight line. But you can see that at least for this particular case, that there are departure from this line at the edges of the data sets. So can you see that it is actually departed from the straight line? So that means there is a departure from normality. So that means the data is not really following normal distribution. So instead of doing Shapiro-Wilk test statistic, or instead of carrying out Shapiro-Wilk test, even if you look into the QQ plot, it should give you an impression that your data is not normally distributed. Okay. So these are the some of the univariate analysis that are of much importance to us. Now, suppose you want to carry out all these analyses, of the variable height, but not for all the people, but you want to carry out this analysis separately for genders. So that we can do. Suppose I choose the gender variable and I use this arrow and write it here. Now this analysis will be carried out separately for each gender. So you can see that. Okay. So you can see that the summary measure, that mean. Now for the female, one value is reported, for male another value is reported. For female, one value of median is reported, for male another value of median is reported, and so on. Similarly, you can see that the two histograms, one for the females and another one for the males. Two different box plots. Can omit the data. Yeah. Two different box plot, one for female, another box plot is for male. Two different QQ plot. So everything now is calculated separately for males as well as females. So all the univariate analysis is done, but separately for males and for the females. Okay. So this is the basic descriptive measures that we can do using the Jamovi software. Now the next
Hello,
thing
sir.
that
I had one query.
Yeah,
Hello.
sure.
Sir, we have got the bar like box plot, QK plot. So can we give the data labels there? Like in box plot, I want the data labels like what is Q1, Q2, Q3. It's not there. Possible not, sir?
That I think I'm not sure. I have to check. Okay.
Sir,
Whether you
excuse me, sir.
Okay, sir.
Yeah.
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 Sir, we had used Shapiro-Wilk here. No, sir. We have around 2,000 participants in the data here. Is
Yeah.
Shapiro-Wilk right to interpret? Is it right to interpret using Shapiro-Wilk alone here, sir? Or would Kolmogorov-Smirnov would have been a better measure?
No. If see, Kolmogorov-Smirnov is applicable. In generally, Kolmogorov-Smirnov is applicable when you want to assess the normality, not normality, but when you want to assess whether your data is coming from some arbitrary distribution. So that may be a normal distribution, that may be some Poisson distribution or something else. So Kolmogorov-Smirnov is basically more kind of what should I say? Kolmogorov-Smirnov is more general kind of testing, which is a non-parametric test. On the other hand, this Shapiro-Wilks actually test whether your data is coming from normal distribution or not. So the best recommendation in this situation is that you try out different tests of normality. Okay, so there are actually other tests also, like this Shapiro-Wilk test, then Kolmogorov-Smirnov test, then Kramer-von Mises test. So there are many such tests, statistical tests which are available. So what you can do, you can perform all these tests and then check what majority of the test is telling you.
Okay, sir.
Okay. In
Thank you.
general, it may happen that one of the tests is telling you that data is not normal. The other test is telling you the data is normal. So in such cases, my recommendation is to try out many different tests and then see what the majority is telling you.
Yes, sir.
Okay. Okay, so this is so far about the univariate summary measure. Now suppose I want to calculate or I want to carry out the exploratory analysis, but not for the univariate data, but for bivariate data. So that is available under this scatter plot option. So is it, are you getting this scatter plot option? Is it available to everyone?
Yes, sir.
Yeah, because it is available under the modules scatter. Okay. Okay. Now suppose I want to draw a scatter plot where in the x-axis I want to draw the height values. On the other hand, on the y-axis I want to draw the weight values. So this will give us the scatter plot. So basically in the x-axis I'm plotting the heights of the individual, and in the y-axis I'm plotting the weights of the individual. Now suppose I'm not only interested in getting the scatter plot, but I'm also interested in finding a linear regression line or a prediction equation which can be used to predict weight based on height. Of course, that may not be the good idea all the time, but at least for the, yeah. So at least for the demonstration purpose, we can check that here. So now you can see that not only the scatter plot, but the linear regression line is also available here. Sometimes instead of working with a linear regression line, we just want to work with a prediction formula which is very flexible. Instead of a prediction formula that is a line, or which is a formula of the form a plus bx, because that is the equation of a straight line. Suppose we want to be flexible, that the formula the formula can be of more complicated form. So there is an option for that as well. So you can see there is a smooth curve passing through the data. So this is basically a smooth regression curve. So this is no longer a straight line. This is a smooth regression curve. You can also plot the smooth regression curve.
What are the benefits of smooth over linear?
The benefits of smooth over linear is that in certain data sets, the prediction equation, a linear prediction equation, may not be meaningful. Suppose your data is, for example, suppose you are increasing dosage of some particular medicine and you are checking the effect of that in a patient. So then definitely it will happen that after certain threshold level, instead of improving the condition, it may deteriorate. So that means your scatter plot would look like a umbrella. The shape would be look like an umbrella. So in that case, if you want to predict the health condition based on the dosage level, and if you use a straight line as a prediction formula, that is definitely not appropriate. So instead, in that case, if you use such a smooth curve, that will give you a better prediction formula. So that is
Sir, is
okay.
Sir, is it the lowest method?
Most likely it is the Lewis method. I'm not 100% sure what they are using inside, but most likely it is the Lewis method, because in most of the software they implement that Lewis method, which is a non-parametric smoother.
Okay. And is splining possible here by any chance? Splining
What?
and
Spline?
Splines.
No, they don't give you the option in the usual form. For that, you may have to install some modules, but I'm not 100% sure whether there are such modules under which you can do the spline regression.
Okay, so thank you.
Yeah. Also, sometimes we are not only interested in the regression line, but we are also interested in the standard error. So you can also see the standard error. Can you see that it is a very thin line? I think you can do it in your own machine. And you can see there is a very thin line, which gives you the standard error of the regression line.
Sir, where can we find the equation of the linear line?
Oh, yeah, right. So that we can find under the option regression. But since we are working under the option exploration, here you won't get any equation. Okay, here you only get the picture, the graphical display, and that's all. But if you want to get the equation of the regression line, that you have to derive it under the option regression. I'll show that.
Okay.
Yeah.
Sir, what is the utility of finding the standard error of the regression line?
Yeah, the standard error of regression line, if the standard error is, so for example, if the standard error is this band, the regression band that you can see, if the standard error is high for the regression line, then the band would be very thick or very fat. So in that case, the regression line that you are getting for the particular data set, when you change your data set, it may get changed a lot. On the other hand, if your standard error is low, that means the regression band that you are working with, if it is very thin, the meaning of that is, if you change your data set, then the regression will slightly change, but it would more or less remain same. So that means the result you are getting, that is more translatable to the population level. So the sole objective of doing statistical analysis is to what you observe in the sample, the particular sample that you have gathered, whether you can translate it to the population level, or which is all the people maybe, or all the person with that particular disease or that particular health condition. Okay. But if your standard error is large, so that means this band will be very large. So that means your regression line can change a lot within that band. So that means the regression equation may change a lot if you change your data set. So high standard error actually means unreliable statistical finding. So that means if you try to translate that statistical finding to the population level, at the population level, the reality may be very different from what you are observing at the sample level. So we would always like to have a standard error which is low, or we would always like to have a regression band which is very thin. Like we are observing here, the regression band is quite thin. Okay.
Thank you, sir.
Okay. So what you can do, you can also look into the, you can add the marginal variables in the same picture. So that means the box plot of height and width here. So you can see this is the box plot of height and box plot of width. So that means in this picture, you are getting the bivariate summary measures like the regression line, the standard error of regression line. These are strictly bivariate measure because this is something related to both height and width, both the two variables. So that's why it is a bivariate measure. On the other hand, you also have certain univariate measure like the univariate box plot. This is the box plot related to height, and this is the box plot related to width. Instead of plotting the box plot here, you may like to plot the distribution or the density or the histogram. So that is doable under the density option. So it is actually giving that smooth version of that histogram that I have showed previously. So can you see that? So it is in a single picture. It represent both the inside in the body of the picture. It is giving you the bivariate summary measure, and at the side, at this two side of the picture, it is giving you the univariate measures or the univariate histogram, or rather I should say the smooth version of the histogram, which is more interpretable. Yeah, there are some questions like how can we calculate ROC curve, etc. All of these things are, and most of these things are doable, but for that you have to install the appropriate modules. And I'll show some of this result, not of course not all of them, because my objective is to make you well versed with this particular software so that we can use this software to carry out time series analysis. So our main focus is to do time series analysis. So I may not be able to answer all this question related to specific kind of statistical analysis, but I believe most of them are available under certain modules. Okay, for that you have to check the appropriate modules. Like these are some of the basic modules, and this is a module Snow Cluster that I have installed. We need that module for doing the time series analysis. Okay. Also, we can do this bivariate and univariate analysis separately for males as well as females. So that is also doable. So it is. So can you see the picture now? So this you can see that the blue dots, those are the plots of height and weight for females, and the yellow dots, those are plots heights and weights of males. And so you got two different regression line. One regression line is obtained for females, the blue regression line. The yellow regression line is obtained for males. Similarly, for the univariate distribution of height for female is given by this curve. The univariate distribution of weight for female is given by this density curve. The univariate distribution of height for male is given by this curve. Univariate distribution of weight for male is given by this curve. So altogether we have 4 marginal histograms, or rather I should say smooth version of histogram in this case. So is it okay?
Yes, sir.
Okay. Okay, so far this is all about the univariate and bivariate summary measure. Now let us go into carrying out t-test. So under this one sample t-test option, suppose I just take this height variable and you can see that it is testing that the height value is 0 versus height value is non-zero. Okay, in this case you can also change the value here. So that means you are now testing that your data is coming from a population whose mean value is 2. So that is your hypothesis, the null hypothesis H naught, and you are testing. The alternative hypothesis is that your height is, or average height is not 2. Okay. Maybe okay. So this will be the test statistic. This is the degrees of freedom, but we are seldom interested in the value of the t statistic itself, but rather we were more interested in the p-value. And since p-value is coming out to be very small, so it is telling that the H0 is rejected. Of course, that would be rejected because in this data set, since it is the data of heights of individual, that will surely be positive values. So my hypothesis that I have hypothesis here that it is 0, that will definitely be rejected. So that is what we are seeing here. Okay. We can also change. You can see that the alternative hypothesis for your null hypothesis also specified here. I can change the alternative hypothesis, and accordingly the p-value and other things will change. Okay. You can also check the descriptive plots, or you can also calculate certain descriptive measure, but these measures are already calculated under the univariate descriptive summary measure option. So, but you can once again calculate them under this t-test option also.
Sir, in one way or so two way, the p-value will not change, sir.
Sorry, can you just tell me the question?
Sir, in one way, it is the test value not equals to test value. I mean, it means 0 is not equal to test value,
Right.
and 0 more than test value, and the statistics remain same, and it is not changing, sir.
The statistic
Means the one sample test.
Yeah, the statistic. Yeah, right. You are absolutely correct. The statistic will always remain same because the null hypothesis is not changed. The test statistic that you are, the test statistic value that you must be talking about this value, right? This 838, right?
Yes, sir.
Yeah, this value won't change. Okay, this value won't change because this null, this test statistic value is dependent on the null hypothesis. On the other hand, if you change the null hypothesis value, you'll see now that statistic will change. Suppose instead of this putting it 0, I put it 1. Now you'll see that it will change. Can you see it is changed?
Yes, sir.
So that means the t statistic value will only change if your null hypothesis is changed. Okay. On the other hand, if you just change your alternative hypothesis, that will be reflected in the p-value. That may reflect in the p-value. There is no guarantee, but that may reflect in the p-value. But the t statistic will definitely won't change.
Yes, sir.
Okay. You can also check for normality QQ plot, so that is possible. We have already seen this thing under the univariate option, but you can also the same picture, the picture that we have got previously, we are getting the same picture. So either you can get this plot, this normality test and QQ plots, all these things under the descriptive measure option, or you can also get them under the t-test options. Is it okay? Okay. Now suppose I just want to, instead of one sample t-test, I want to carry out the paired sample t-test. Actually, paired sample t-test is meaningful when we have a data set where the observations are obtained in a pre-post manner or in a paired fashion. Unfortunately, this is not a suitable data set for carrying out the paired t-test, but still for the sake of demonstration, I just forcefully assume that this height and weight, they are like the paired observation of same variable, which is definitely not true. One is the height variable and another one is measuring weight. But for the time being, for the sake of demonstration purpose, we're just assuming that they are like the paired value of the same variable measured in a pre-post fashion. Okay. So you just select both of them and then push this button. Can you see that the two variables are selected in the right hand side, and that will give us the ART test. And you can also see the alternative hypothesis that the mean value of the pre-level and the mean value of the post-level, they are not matching. You can, if needed, you can also change your alternative hypothesis in this case. Now, suppose you know that your data is not really coming from normal distributed variable. So in that case, sometimes it is better to avoid t-test. Okay, and instead of t-test, what we can do, we can perform the Wilcoxon rank sum test. Okay. So there we are calculating the Wilcoxon rank sum test. Okay. Under the t-test option, you can also perform the independent sample t-test. But for the time being, I'm not showing you the independent sample t-test. I'll show you using another dataset. Show you that using another dataset. Now let us directly come to the regression part.
Sir,
Yeah.
Sir, can
Yeah.
you please repeat the PRT test where we selected two variables?
Okay. Okay. Sure.
Can you explain that part again?
Yeah. So let me start from the scratch. So suppose I want to compare this height variable and the weight variable together. So what you do, you press the control button and press both of them. So that means both of them are selected simultaneously. And then you just use it to drag here in the right hand side, and that should give you the paired sample t-test. Can you do it in your machine?
Yeah, I can do it, but my confusion is with the interpretation. How will I interpret this thing?
Oh,
What will be my
interpretation. Okay. So by interpretation, so if the p-value is very small, so that means there is significant difference in the pre-level and the post-level. Suppose you are,
I mean, sir,
yeah.
in case of pre and post, we usually
Yeah.
do something like, oh, okay, we are assuming here are two. I mean, suppose we have a group of students and we have
Right.
given some supplementation. Now I am checking their weight. So I have pre weight and post weight.
Right.
So I want to compare that, but here we are taking height and weight. So
yeah. So yeah, that's what I have told you, that actually ideally in place of this height, you should have the weight before giving the
pre and height
supplement.
post.
Right. Height
Okay,
pre
okay,
and height
okay,
post.
okay.
And you
Okay,
drag
sir,
both of them together, and then you can carry out the
Okay,
pair
sir.
sample t-test. For this
Understood,
particular
understood.
example, I'm kind of forcefully doing this. It is actually completely meaningless because you are comparing between height and weight, which are completely different variables. So
Understood, sir.
yeah. So this is just for demo purpose. Okay.
I wanted to ask, suppose in this t-test,
yeah,
when we are taking pre and post values,
right,
do we have to check a normality for both the parameters, both the
right.
pre-test
Yes,
parameters and
yes.
post-test?
Both of them. Yeah, you have to check that.
But here when we are putting this normality test, it's showing, I think, only one. I don't know, it's showing some strange results. I just tried and put the normality test. It was showing something. It was only one p-value was getting shown.
Right. I understand. I understand what you are getting. So actually, yeah. Now it is clear what you are saying. So you'll see this only one p-value. What is the meaning of? This one p-value is not related to separately. They are not reporting it separately for the pre-value or the post-value. But what they are doing, they are taking the difference of the pre-value and post-value and considering that as a single variable, the difference, and then performing the Shapiro-Wilk test on that. So that's why you are getting only a single p-value.
In case of independent samples, how do we get it? Do we get separate or?
There you will get, in case of independent sample, you will get two different p-values. For the case of paired sample, what they are doing, instead of checking two different normality tests, what they are checking the normality of the difference of the two levels. So that's why they are reporting only a single.
Okay, sir.
For two sample, it will definitely be two p-values. Yeah, I got question. Yeah. Okay, so now let us move to the regression part. So suppose I just want to talk about the linear regression. So someone from you was asking how to get that equation, right? You are asking that. Suppose this is the weight, that was the dependent variable, weight was plotted in y-axis, height was the independent variable. So I just want to put height in the x-axis, and in factor variable, I'm not putting in anything for the time being. Okay, I'll put it later. You can also perform certain tests of normality, autocorrelation tests. These are actually kind of diagnostic tests while performing linear regression. So you can perform that. You can also perform the normality test. You can also check the Cook distance, which gives you an idea about whether there is some outlying observation in the data, which is heavily influencing your finding. Okay. So you can do all these things. But I'm interested in finding the equation of the regression line, right? Yeah. So can you see that this model coefficients, actually that is giving you the estimate of the regression line, the equation of the regression line. So it would be like minus 135 plus 130 times height. So the equation, the prediction equation for predicting weight based on height should be read like this, that the equation would be minus 135 plus 130 into height. So is it now clear? I think someone was asking how to get the equation of the regression line. So that can be derived under this linear regression option. It also gives you the standard error of each coefficients. It also gives you the confidence interval, the lower value for the confidence interval for the intercept, the upper value of the confidence interval for the intercept. It also gives the lower and upper value for the confidence interval for the predictor variable, which is height in this case. And it also give you the p-values. And under this T column, this actually give you the test statistic value. We are not really interested in the test statistic value, rather we perform the testing using the p-value. Someone can perform the testing also based on the t-value, but that will be, of course, more cumbersome, because you have to look into proper statistical table, find proper cutoff, and perform the test based on that. So p-value is relatively convenient, so we generally look into the p-value. So these are certain goodness of fit measure of the model. So it tells you that while doing the linear regression or while fitting a regression line, how good the regression line is fitting in your data. So this is actually described by this measure called R square and adjusted R square. So can you see that the R square value is 0.214, which is very small. So that means it is not really a good fit. Ideally, a high value of adjusted R square should tell you that the underlying regression model is good. Okay, but as it is being described by the value of the adjusted R square, that the regression line, although we can find an equation of the regression line, we can use that equation to predict, but it may not be a good prediction formula because the regression line is not fitting well to the data set. So it is evident from this model fit measure. So the model is not fitting well to the observed data. So that means a linear regression may not be suitable. You have to work with some other kind of regression. Maybe you may have to use data transformation, or you may have to use lowest regression or some other kind of regression. So is it okay?
Yes,
Sir,
sir.
can we get
Sir,
the
can we just
can we get the regression plots like the so that we can understand whether there is homozygosity or some kind of correlation? So when automatically can these plots come?
The plots means are you talking about the correlation plots or something like that?
Yes, like the like residual versus the original values. That like to see the homozygosity or the autocorrelation. Those diagnostic plots actually.
But here there is no option of getting the plots. They will just give you the t statistic p-value in the table form.
Okay, sir.
You can of course get the residual plots, but you can get the residual plot.
Okay, sir. Okay.
In this way, but not any testing in or not any test statistic presented in a graphical form. That is not given. Everything is given in the form of a table. So this autocorrelation test, the normality test, and other kind of testing. So they will report some p-value for that only, not any graphs.
So just can you repeat that regression part from 1 second in a short?
Yeah, sure. So let's start again that my dependent variable or y is weight. So I push the weight into the dependent variable part, and then I push the height variable as the covariate. Now I just want to get the regression line, and the equation of regression line is obtained under this model coefficient option. Okay. You can also get the confidence interval. So you can also get the confidence interval. If you just uncheck the confidence interval, it will just give you the estimate of the regression line. So that means it will give you the equation only. But we are sometimes interested also in the confidence interval, so you can get that also. Is it okay now?
Yes, sir.
Also, you can add factor variable. Like in this case, I want to carry out regression of weight on height, but not in the combined form, but rather separately for gender. So I want to take the gender factor into the model. So that can be done by pushing the gender under the factor column. So you can see that it will give you now it will give you some regression line, but it will also accommodate gender as a factor variable in your model. Okay, it's actually not exactly same as the performing regression separately for males and separately for female, but it's something different. It's actually performing regression accommodating the factor that a particular subject may be a male or a female. That okay. So then you get such a particular table for the test. Okay. Okay. So this is about the regression. We can also look into something called the correlation matrix. Suppose I just want to calculate the correlation between height, weight, and age. It is actually giving you the correlation matrix. Can you see that? These are the correlation values. So this gives you the correlation between height and age, this minus 0.027. If you want to calculate the correlation between the age variable and the weight variable, it is given here 0.203. And then if you want to calculate the correlation between height and weight, it is coming out to be 0.463. So this will give us the correlation matrix. Is it okay? Instead of working with the Pearson correlation, you may be interested in calculating the Spearman's correlation. So it is not only, in this case, it is not only giving the Pearson correlation coefficient, but it is also giving the Spearman's correlation coefficient. So now it is giving only the Spearman's correlation coefficient.
Sir, can you explain the results of regression tables that you derived at? I didn't understand much, sir. That
okay.
So can you please scroll up?
Yeah, sure.
No, sir. So down, sir. Down.
Yeah.
Down further. Yes, sir. The gender male, female. Sir, how do you understand this table, sir? Can you, sir, for example, I've understood intercept part, which is the A part of the equation, and height would be the predictor. That is the X part, right, sir? Not the B part.
Right.
And the gender male, female minus 10.5, sir. Can you explain that? I mean, how do you make a sense of this number?
Yeah. So one of the level is coded as 0, and the other level is coded as 1. So when you add the value of when you suppose in particular equation, suppose someone's height is X. So how would you calculate the weight of that person? So that will be minus 188.6 plus 164.8x plus minus 10.5 in case it is a female. On the other hand, if it is a male, this will be 0 into minus 10.5. So there is no contribution from that part.
So that means male is a reference and female, this is the value for female.
Right,
Is that
right. Yeah, right.
Okay, so. But how did you know that, sir, male is reference? Did you put anywhere, sir, that male is a reference and then we are computing for female?
So that would be evident from the picture. So from the picture, you will see the regression line. From there, you will see the difference in the slopes.
So can you demonstrate, sir?
Can I help?
Yeah.
So actually, like as there are two levels only, so basically when you go from one level to another, the change of value is the slope. Okay. So here, if you look at the coding, sir, if you please come to the coding once, male and
part?
female, the like the data set where male and females are coded.
Is this one?
So the variables where
So
we
this will
coded probably
minus 10.65. That value is added in this equation, this male part. No, we haven't coded the male female. We coded in a new column actually. We haven't coded the male female in the original for the original variable.
Okay.
So in generally they code it in the form 0, 1. So that is the convention. Now here you can see that for a typical the height for a typical male is coming out to be lesser compared to the height of a typical female. Sorry, the weight of a typical female. So that means the minus 10.65 part will enter into the equation for the male, and for the female candidates, it would be 0 into minus 10.65. I think minus 10.65 or so. Yeah, sorry, minus 10.5.
So that means the predictors and the factors both are same here.
So what is your question? So please can.
The predictors means the covariate and the factors both are same here.
No, they are not same. For the predictor value x is same for both a male and a female, but for the female part, 0 will be contributed here. For the male part, minus 10.5 would be contributed.
So that means the gender here it is considered as the predictor, sir. That is not the factor, sir.
Yeah.
Okay.
No. So actually, it is a factor which is used for the prediction. So in that sense, it is also a predictor, but it is not a numerical predictor variable. It's a factor predictor variable.
So can we therefore, in this case, can we say that when we are sort of controlling for height,
right,
males, the average weight of males is 10.5 kilograms lesser than the average weight for females.
Right. And that is also evident from that picture, that if you take any typical height and look into the a male having that particular height, his typical weight would be predicted by this value here on this prediction equation, which is a straight line. And for a female with the same height, her typical weight would be predicted by this blue line. Okay. Is it okay?
So, sir, in this model that we sir Dr. Inamul Haq very beautifully explained. So in this model, so one predictor is height and one predictor is gender, but then we control for height and then look at the effect of gender on the dependent variable.
Right.
And okay, so sir, how do we check out if there is interaction between these two?
Interaction between
these both the predictors.
Both the predictor. Yeah, actually in this case, you cannot really calculate the correlation because one of them is basically a nominal variable and the other one is a numerical variable. But had this been had the two predictor being numerical variable, you can easily check whether they are correlated or not by using their correlation between the predictors. Okay, that is possible.
Okay, sir. Thank you, sir.
But in this case, you cannot do that because one is category, the other one is numerical variables. You cannot calculate correlation coefficient, but you can of course perform other kind of test, like there are other test of independence. Okay, there are other tests of independence, chi-square test. You can perform those kind of tests to see whether they have interaction, the gender and height has any interaction. You can perform the chi-square test.
So to look for association.
Right, look for association. Okay. Is it okay? Okay, so maybe then I can demonstrate. I can open a new data set, data library. Can you see the new screen? I open a new data set. All of you can open it. Just go there, press the open button, go to the data library part, and under this data library, you will see that there's an option of iris data, which is a classical data set on measurements of flowers. So you can just select that data set, and I have selected that data set to show a few more multivariate analysis. Okay.
Sir, what is the name of the data set?
That is iris data set, Anderson's iris data set. Under this option, you go to the open and then go to the data library, and you will see this option, Anderson's iris data set. So this is a classical data set on measurements on flowers.
Sir, your screen was freezed, sir.
Oh, is it not being presented? Okay, just stop and then rejoin. So, now I think you can see it, right? The new data.
Yes, sir.
Sir, can you repeat it again?
So just go and open, and under the open option, you can see that if you click the data library option, there you will see they are showing some data sets, options of some data sets which are the part of the Jamovi installation. So one of such classical data set is the iris data set. So you can click on this iris data set. Now we are working with this iris data set. Okay. Once again, we'll just again go back to that correlation matrix calculation. So there are many variables. So suppose I'm considering these three variables, and I just want to calculate the correlation matrix for this three variables. You also have an option of plotting the correlation matrix. So there are three variables. One variable is the sepal length, another variable is the sepal width, and another variable is the petal length. So these are basically a data set on flower measurements. Now, these two variables, they have some correlation, and these two variables, they also have some correlation. So this actually give you the scatter plot of the sepal width and the sepal length. So these two variables, the first variable and the second variable, if you look into the scatter plot of that will be given by this picture, this sub picture, I should say. Similarly, if you want to look into the scatter plot for the sepal width and petal length, you will see that here. So this will be a picture that is obtained by the scatter plot of the second variable and the third variable. Similarly, this one will be given by the scatter plot of sepal length and petal length. So the first variable and the third variable. Can you see that? You can also plot the correlation inside this matrix. So in one panel or one part of the matrix, it will give us the scatter plots. In another panel, it will give us the correlation values. Can you see the correlation value? So minus 0.118 and 0.872 and minus 0.428. You can also plot the marginal densities. So this is actually the histogram of the sepal length or the density plot of the sepal length. This is the marginal density plot of the sepal width, and this is the marginal density plot of the petal length. So in this way, in a single picture, you can get both the scatter plot as well as the marginal density plot as well as the correlation coefficient. Actually, this is a very nice form of the correlation matrix where you get both the univariate pictures, the bivariate pictures, as well as the bivariate summary measures. So this is actually very useful in assessing relationships of multiple variables in a single data set. Okay. So you can see that there is a good relation between the first variable and the third variable. So you can also check it from the correlation coefficient, that the correlation between the first variable and the third variable is coming out to be 0.872. Okay.
Sir, can you please repeat the graph which
Yeah.
shows the correlation between each two variables?
Right. Okay. Yeah. So this graph lie in the intersection of the sepal length, this column, and the sepal width, this row. So that means it is a scatter plot related to the first variable and the second variable. Similarly, if you look into this graph, this lies in the intersection of the first variable and the third variable. So it is a scatter plot of between this variable sepal length and the other variable petal length. And sepal length and petal length, they are very much correlated. You can look from the scatter plot itself that it is very much concentrated around a straight line. So that means actually they is a very high correlation between sepal length and petal length, and actually it is expected. Okay. Also, this third picture, this gives us the scatter plot for the second variable. So the second column and the third row. So that means the second variable and the third variable, their scatter plot is given.
Got it, sir. Thank you.
Yeah. Okay, you can also get the density plot. Finally, I just want to show you the one-way ANOVA. Suppose I want to carry out one-way ANOVA of sepal length. This is my dependent variable. And in one-way ANOVA, you know that there are multiple groups. So suppose I want to group the observation according to the species. So there are actually 3 species. So 3 plant species have been considered in this data set. So there will be 3 groups, and I just want to carry out one-way ANOVA analysis of the variable sepal length according to different species. So there are options of the conventional ANOVA. So you can perform the conventional one-way ANOVA test, and this will be the p-value. You can also perform the Welch-ANOVA test, which is applicable when your variance of the data varies according to group. In that case, we should not work with the usual Fisher's ANOVA, but in that case we should work with the Welch ANOVA. Okay. You can also check the homogeneity test. So this gives us the Leven's test for homogeneity of variance, and as it is evident that the same variance, all the three groups have same variance, that is rejected. So that means we really cannot apply the conventional ANOVA, which is the Fisher's ANOVA, but we should apply the Welch ANOVA, which assume the unequal variance. We can also, and also it is evident that there is significant difference of the sepal length according to the groups. So the p-value is very small. The H0 hypothesis that the three groups are same, that hypothesis is rejected. There is difference in sepal length in terms of different groups. So that is evident from this table. Now, once your H0, that all the groups are same, that hypothesis is rejected, then the next question that we ask, which are the groups which are same and which are the groups which are different? So there is a possibility that you are considering 4 groups. Now there is a chance that all the 4 groups are different to one another. So then also, if you perform a one-way ANOVA table, it will show that there is a significant difference. On the other hand, consider another situation where among the 4 groups, 3 groups are very similar to one another, but the 4th group is very different. So in that case also, the one-way ANOVA will tell you that there is significant difference. But the one-way ANOVA table is unable to distinguish between these two situations, where all the groups are different from one another, and when all the groups except one is different. Okay, so there is no way to differentiate between these two situations based on one-way ANOVA table. In that case, we know we carry out the post hoc test, or which is also sometimes called the multiple comparisons. So in this case, the usual post hoc test.
Sir, can you please repeat this part where you cannot use the one-way ANOVA?
Yeah, the thing is that when you click this homogeneity test button, it is telling you that the homogeneity of the variants are homogeneous in the 3 groups. There are 3 groups, 3 species. And if you consider the data variability in each of the 3 groups, my hypothesis is that their variation is similar. But if you perform the Leven's test of homogeneity of variance, it is giving you very small p-value. So that means your H0 is rejected. So the meaning is that the 3 groups are different in terms of their variability. One may be highly variable, another group is very less variable. So in that scenario, you really cannot apply Fisher's ANOVA, one-way ANOVA. So you can see that there is a prompt is written that assume equal. So assume equal variances. So, but unfortunately, the Leven's test is telling me that there is not equal variance among the 3 groups. So that's why I cannot go with the Fisher's ANOVA, but rather I should work with the Welch ANOVA. That is what I have to. I'm just telling. Yeah. So one-way Welch ANOVA. So can you see that? Okay.
Yes.
Yeah. Yeah. So then you can perform the post hoc test, which is the Tukey test. But however, see that Tukey test is applicable when you have equal variance, but you already have seen that the Leven's test is telling you that no, the variances are not equal. That's why you haven't performed the Fisher's ANOVA, but rather you have performed the Welch ANOVA. So under this situation, it is not appropriate to consider the Tukey test, but rather the other alternative test which is given. There are actually many such tests. So this is many such tests are there. So in this case, we perform this particular post hoc test, and that is again telling me that the first group, what is the difference between the first group and the second group. There is significant difference between the first group and the second group. It is telling me there is significant difference between the first group and the third group. This is also significant. And then it is telling me that there is a significant difference between the second group and the third group. This is also significant. So that means all three groups are significantly different from one another. So that means all the three species, they are significantly different from each of one another. Okay. So this is all that I was supposed to explain you using this Jamovi software. So we have seen that using the Jamovi software, we can do basic coding of the data. We can calculate, or we can create new variables from the existing variables. Then we can calculate summary measure, the univariate summary measure. We can also calculate the bivariate summary measure and corresponding graphical plots. We can perform t-test. We can perform the one sample t-test. We have already seen that. We can perform the paired sample t-test. We have also seen that. We can also perform the independent sample t-test, although I haven't shown that here, but you can easily perform it. Then we have seen that, but the t-test is applicable only when you have the independent sample t-test is applicable only when you have two groups, like male, female. However, if you have three groups, like this particular data set, when you have three groups, three species, in that case, t-test is not applicable, but you have to move to one-way ANOVA. We have seen that how one-way ANOVA can be done using this Jamovi software. And this is one-way ANOVA, the usual one-way ANOVA, parametric one-way ANOVA. There is an option of the non-parametric one-way ANOVA, which is also known as the Kruskal-Wallis one-way ANOVA. You can also perform that. I haven't demonstrated that, although. And similarly, you can also perform the regression. We have seen how to calculate the multivariate correlation matrix, or the matrix scatter plot for multivariate data. We have also seen how to calculate the linear regression. We haven't seen the calculation of partial correlation, but I think you can easily do it. Similarly, there are other type of regression options available, like you can perform the logistic regression, that is possible for two-class logistic regression, and then there are multi-class logistic regression. There are option of ordinal regression. All these things can be done. I haven't demonstrated although. So these are the analyses that we have considered here. And then there are extra modules installing which you can perform the suitable kind of statistical analysis for your research. Like, for example, for this particular course, I have to carry out time series analysis. And that's why I have installed this particular package, the Snow Cluster package. Okay, so you need to install this particular package for carrying out time series analysis.
Sir, in the modules, where is this Snow Cluster? Just can you guide us?
Okay, so you go to the Jamovi library. So search, you can also search here, Snow Cluster. So it will show you the Snow Cluster. Can you now get the Snow Cluster package and install it? In my case, it is showing install because I have already installed the Snow Cluster.
Yes, sir.
So it is showing in your system, right?
Yes, sir.
Yeah.
Snow Cluster multivariate analysis.
Right. So you can install it, and then in the third class, where we'll be using Jamovi to do statistical analysis of time series data, there this package would be useful to us.
Sir, we have worked in two datasets.
Yeah.
I'm not getting any save option. So what is
Yeah.
about the saving this
Right.
works?
There is an option for save. Right. Yeah, I forgot to mention that. Go there. There is an option for save. So that means if you now save it, or maybe there is an option of save as. Now in this PC, maybe in desktop, or maybe save option. Save option. So you can, under the save option, you will be able to save it as a Jamovi file. So there is a file extension, the particular file extension for Jamovi file. So under day one, open. Sorry. Yeah, it saved something like that. Okay, so and then if you just want to save the output, you have to export that. Just under the export option, you'll see a button called export. There are certain options like you can export everything in the form of a PDF or some other file also. It is possible, but I'll export using the PDF option. I can export it. So just let me check whether it is exported correctly. My system. Yeah. So after exporting, yeah, you will get such a PDF file. You should be able to get such a PDF file. Have you been able to save it in your system?
Yes, sir.
Yeah. So by exporting, you can save it in the form of a PDF. And on the other hand, if you save it, then it will be saved as a Jamovi file. So that means whenever you open inside from inside the Jamovi software, it will give you this particular data set, and all the corresponding analysis will be presented that moment. So you can also save it in that form, or you can save it in the form of a PDF by using the export option. Okay. So with that, I think maybe we can stop here for today. And so if you have any query, so please ask me. So I think there are some questions, like maybe just quickly go through the question. How can the quantiles be negative? How to export the output of? Okay, so are all these functions are in, we need to install some dependencies. No, you don't need to install any dependencies, but you may have to install some modules for performing suitable statistical analysis. So can we plot RSC curve? Yeah, Okay, so you may ask related to today's class.
Sir, I have a very fundamental questions regarding regression.
Right. Sure.
Sir, what is the difference between the residual and the error?
And what is the difference between the residual and error?
Yes.
Okay. So error is like something which is hypothetical, and residual is what you are observing in your sample. So in a sense, you can say that the errors are the corresponding object in population, and their sample version is the residual, in a sense.
Sir, please repeat.
So in a sense, you can say that the errors are the object related to population. They are hypothetical in nature. On the other hand, I mean, there is no way to calculate the actual value of an error. It is not possible. On the other hand, the residual is something that is available to you because it is based on the data set. So it's like the sample version of the error. Like population mean is a hypothetical object. We are always interested in the population mean, but unfortunately we can never get hold of that. On the other hand, we always have a sample and we have sample mean. So sample mean is like the object that we can get access to, and the population mean is the object that we want to get access to, but we cannot get access. So it's like the proxy for the population version. So similarly also the residual is a proxy for the error. The error, you can never get an idea about the error because it is related to the population. You cannot enumerate the whole population anyway. So that is never possible. But however, you can get a representative sample from the population, and from based on that, you can calculate the residual. That is possible.
Sir, what
Sir,
is the
then
utility? Go ahead.
Sir,
Yeah.
if there is a 95, the shadow line, 95 confidence level, the shadow line, then it
Right.
should represent the residual, not the error, I think.
Right.
If you can predict the residuals, then I think the shadow line, both the above and below the regression line, it should be on the basis of residual.
Right. So it is based on the residual, and it is also based on the sample only.
And these are not based upon the standard error, right?
Standard error. Standard error means something else. Are you talking about the standard error or the model error?
Sorry. I am talking about the model error.
Yeah. So right. So in that case, it is not based on the model error, but it is based on the residual. Model error is basically a hypothetical object.
Okay, sir. Got it.
Yeah.
Sir, a follow-up question to what was asked just now. What is the utility of calculating the standardized residual?
Yeah, the utility of standardized residual is that in certain kind of regression technique like logistic regression and some other regression, the usual residual is not meaningful. I mean, you cannot interpret them whether the residual is showing that the model is not fitting well or there is a departure from normality. To perform that kind of test, you need to standardize the residual. And that standardization is, again, there are many different ways of standardization. Depending upon that, you may come up with different type of residuals. Okay.
Thank you, sir.
Yeah. Okay. So if there is no more question, can we end today's class?
So the thing about the quantile being negative.
Yeah, sure. So what was that? Quantiles for what?
In the QQ plot, I noticed that in the x-axis, the theoretical quantile can be negative also.
Yeah, the theoretical quantiles, right. You're correct. The thing is that when we are calculating the quantiles, we are not really calculating the quantiles of the original data, but we are calculating the quantiles of the standardized data. Like we are So maybe I can. So can you see the whiteboard? New whiteboard. Yeah, can you see the whiteboard?
Yes.
Okay. So it's like these are your usual data, which is a positive quantity. So if you calculate the quantiles, then they will definitely be positive quantities. However, generally what is done that it is standardized, and then quantiles is calculated based on this transformed data. Now this transformed data can take both the positive and negative value, and that's why the quantile is coming out to be negative.
Thanks, sir. Thank you very much.
Okay. So if there is no more question for today's class, so we can end today's class then.
So thank you, sir. Thank you for the wonderful session. I think you started from the basics, which will be very useful for most of our participants as well as us. So we look forward to your next session that is scheduled on day after tomorrow, that is Thursday, 12 December from 7:30 p.m.
Okay.
Okay, have a nice good night. See you day after tomorrow. Thank you very much, everyone.
Thank you, everyone.
Thank you, sir.
Thank you, sir.